we said that was V of I is min or max of A in AI of R of IA plus beta summation J in E P of IAJ times Vj for all I in E. So we said that that was the Bellman optimality equation, and we said if you solve this equation, you'll be able to find the optimal values. So this is what we said. Or Bellman showed Bellman proved that by solving the optimality equation, we can find the optimal value for each state, which leads to the optimal policy. Okay, so that's what Bellman said. This is nothing but a linear system of equations. It's just a procedure, just like how we solve, simplex algorithm or the simplex method for finding optimal values in linear programming problems. This procedure is very straightforward, really. Okay, all we need to do is solve these equations. It's called the Bellman optimality equation. They don't call it Bellman optimality equation in the textbook. They call it the fixed point theorem, but the idea is really the same. Okay, so the Bellman optimality equation really gives you what are called the fixed points or the optimal values. But what Bellman did not show, or what Bellman did not give, is a procedure to solve the optimality equation. The procedure to solve the optimality equation was not provided by Bellman. Okay, what all he did was he mathematically proved that the moment you solve these bunch of linear equations, there's nothing but a bunch of linear equations, and we'll see that when we solve a problem. You'll see how these are really just simple mathematical equations. Okay, but what he did not give is a procedure for us to solve. He proved it mathematically, but what fun is it when you cannot really solve for these equations? So what Ron Howard did, Professor Ron Howard, again not the movie director, okay, Ron Howard provided a iterative procedure to obtain the optimal values which lead to the optimal actions in each state. Okay, because that's really the goal of solving these equations. Okay, you want to find the moment you wake up in the morning, you turn on your car, and your car falls in one of the 5 states. You want to be able to make a decision whether to take it for repair or not take it for repair. Those were the 2 decisions, right? Repair or not to repair. Do something, do nothing, or repair were the 2 decisions that you had to take. So the idea is to be able to find an optimal policy, which is the optimal action. Your optimal policy okay, the optimal policy is a collection of actions, and we talked about car being in 0, 1, 2, 3, 4, or maybe just 4 states, right? So you want to be able to find the optimal decision, like do nothing, repair, do nothing, do nothing, and repair. This could be an optimal policy. So we want to be able to find that final optimal policy for the given states of the system. Okay, that's really the goal of Markov decision process. So what Ron Howard did was provided an iterative procedure to obtain these optimal values. Okay, so that's what we'll learn today. Okay. I think before we go there, it's very important for us to get an intuitive perspective. I posted a handout online. It's called MDPs and Bellman Optimality Equation handout. I posted it last week. And that really gives you some practical examples of MDPs as well as the intuitive perspective of what this equation is telling you about. What is this equation? Okay, that's why it sort of describes it in plain English, and I want you guys to read that very carefully. It's a very important handout. Okay, and the first part of the handout, I think the first 10 pages, gives you the first chapter of a textbook from Markov decision process that talks about some practical applications of MDPs. Okay, how you take a system and divide that system into states and develop your action space and try to solve a realistic type of problem. Okay, so I want you guys to look at that very carefully, because on the exam I might give you a scenario and ask you to develop, the states, the actions, and sort of cast it as an MDP problem. Okay, so I want you to read that handout very carefully. And there's several examples for pavement maintenance, even in biology. So there's all kinds of examples. Just like how we studied Markov chains, different examples. This handout is intended to provide you guys, the basic uses of MDPs. Okay, so what I want to do now is let's look at the intuitive. This marker is dying on me. Okay. You want to talk about the intuitive perspective of the Bellman optimality equation. Okay. What I want you guys to focus now on is these terms. Okay. What was this? This was what we called the immediate reward or cost, right? And this we said was the discounting factor. Okay, and this was the probability of going from state I to J by taking action A. And this guy was the value function at state J. Okay, we said that's what those terms were. But now for us, let's sort of split this equation apart. I want you guys to focus your attention only on this portion for a second. Okay, so all this says is beta summation PIAJ Vj. Okay, if you forget this if you forget this beta for a little while, what does this look like? What does that look like? If you forget the beta for a little second, you have a probability times a value. What is that in using your knowledge of in the class so far? What is that called? You're taking a probability and multiplying it by a value.
Similar to finding a pi?
Sorry?
Similar to finding a pi? Or like
think a little more. Think a little more. You're sort of thinking in the right direction. Sort of the pi times f, but what is that term called? We gave it a name, right? The expected value, just the probability times the value, right? That's the expected value in this state. Okay? So this is called the expected value in the state J. Because you make a decision, you go to another state, what is the value of going to that state is what this is telling you. But where is this value? This value is in a future state, in a future time period, right? If you want to bring that value to the present, you want to use a discounting factor. Are you guys with me? What do you do in engineering economics? If you have monies in the future, if you want to bring it to the present, what do you do? What do you do? Use a discounting factor? Isn't this what you do? P, find P given F, I%, N. This guy is nothing but your beta. That's your discounting factor. Because the value of money today is not the same as the value of money tomorrow. Right? So you want to use this discounting factor to be able to bring the future value of money into the present time. Okay? So all this boils down to this whole term is called the expected discounted reward or cost. You guys with me? Now I want you guys to look at this term right here, the R of IA. What is the R of IA? That's the immediate reward or immediate cost. Okay? So you're really adding the cost now and the cost of taking the decision in the future. Right? It is all possible costs or rewards associated with the system by taking a given action in a given state. Everybody with me so far? So all you're really trying to do using this equation is trying to find in a given state which action gives you the lowest possible cost or the highest possible reward. Because you're either minimizing or maximizing, right? So all you're trying to do, think again carefully. You have the discounted reward that you're bringing to the present, and you have the cost or reward associated with the current state and the current action. So you add them together, and that's all there is to it. That's the total cost or the total reward for the system. And you either want to minimize that guy if it's a cost or maximize that guy if it's a profit. Okay? So what we want to do now is develop this procedure that Ron Howard gave us to be able to find these guys, find the optimal values which lead us to the optimal actions. Okay? That's really the goal of this whole procedure. Okay? That's sort of the intuitive perspective. It's very straightforward. It's very important for you to understand what that equation is and how it came about. All you're trying to take is the current reward or the current cost and discount the future reward or the future cost to the thing, add them up and see which action gives you the lowest. Okay? So what I want you guys to write down now is the value iteration algorithm. So like I said before, Bellman only showed mathematically what this equation is, but he did not give a procedure to find it. So Ron Howard developed a couple of procedures. First one, what we look at in this class are called discounted value iteration and discounted policy iteration. Okay, we look at two procedures that we want to use to be able to find the discounted value or the discounted policy. Okay, so this we'll look at in the next class, policy iteration procedure. But both of them lead to the optimal policies and the optimal values. In discounted value iteration, I'm iterating over a value. In discounted policy iteration, I iterate over a policy. Okay, this is called the approximation to optimality. It has been proven to obtain optimal solutions, the value iteration procedure. The discounted policy also obtains optimal solutions. Okay? This is a very quick but tedious to compute. There's a lot of computations involved. This is relatively easy to compute. Okay, and it's very easy to write. If you want to write a mathematical code, if you want to write a code, MATLAB code for it, this is much more easier to do than this guy. Okay. Okay. Discounted value iteration algorithm. What is an algorithm? What is an algorithm? It's a procedure, right? It's a stepwise procedure to carry out some computations, right? Which has to terminate at a point, it has to begin at a point, and it goes step by step. That's all it is. That's the algorithm, right? So just like any other algorithm, even this algorithm has to begin So let me give you an intuitive perspective of the value iteration algorithm. What it begins with is a value function. Let's say we have state 0, 1, 2, 3. These were the states we talked about last class, right? The different states of the car. So what we want to do in value iteration, don't write this as step 1. This is not step 1. I'm just explaining what this is. What you do in value iteration is you begin with some random values, let's say 0, 0, 0, and then you iterate, you learn iteratively. This algorithm approaches what are called the optimal values. This could be, I don't know, 95.6, 85.4, 100, 2000. It doesn't matter. You'll have some values at the end of this algorithm, and these values give rise to the optimal policy. The optimal policy could be, if this is the value, we'll identify that the action to be taken is do nothing. If this was the case, it could be do nothing. This was the case, it could be repair and repair. Just an example. Okay? So we'll begin with some value, we'll end with the optimal value, and that value will lead us to the optimal policy for that problem. Okay? That's just to give you an idea of how we're going to go about it. Okay? So any algorithm begins with initializing the parameters. Initialize the iteration counter n equals 0. Write this stuff down, guys. It's a little different in your textbook. Initialize the iteration counter n equals 0. Initialize the discounting factor beta, or not really initialize, just say define the discounting factor beta. And you can take beta, this will be given to you, the rate of discounting. Let's say it's 0.95, the rate at which you want to discount the future monies to the present. And then you want to define what is called the termination criterion. Okay? What this means is, when do you want the algorithm to stop? Okay, because when there is a procedure, you want to stop somewhere, and you want to ideally stop with the optimal value. So this termination criterion is called epsilon, and I want to give it a really, really small value, 0.001 or 0.01 or 0.05. Okay, so these are three things, and obviously we have to initialize the the value function vector, which is v at step 0 will be 0, 0, 0. As many states there are, I just want to initialize it with 0. Okay? The value function vector, the v here, is what we want to initialize, this guy, because we want to really develop an iterative procedure, right? So we want to initialize it with a particular value. Okay? Just be right. Okay. So that is step 1. Step 2 is v n plus 1 of I is minimum or maximum, a in ai, r of ia plus summation, beta summation j in e, p of ia j, and vn j. Okay? Observe this very carefully. This is n plus 1 and this is n. If you see here, you don't have a superscript here because this is not an iterative equation. Okay, you don't have any iterative parameters there. Okay, so all I did was really, I'm saying now that your value, let's say in step n plus 1, will be based on what you had before. So you're sort of, iterating over your value. Okay, that's the idea. And obviously we want to do this for all I in E. Okay, you want to iterate over all states in your system. Okay. Step 3 is check if v n plus 1 I minus vn I is less than 0.001, or really less than the epsilon, which is your termination criteria. Okay, if you find it, if yes, stop and go to step 4, else go back to step 2. Okay. Finally, step 4 is AI belongs to argument. Let me write it a little to the left. AI okay. So you want to be able to find your action function using this, and this AI will be the optimal policy. Okay, so it's really a short procedure that we want to use to be able to compute. And you want to here go back to step 2. Before you go back, you do n, set n as n plus 1. Just write this here because you want to update the iteration counter before you go back to step 2. Just add that as part of step 3 here. If it's no, you want to go back to the step, but you want to update your iteration counter before you go back. Okay.
N is what?
Sorry? Initially n was 0. I want to update it, n equal to n plus 1. Just like your for loop, how you want to increase your iteration counter.
So n is going to become n plus 1?
The n plus 1 is going to become your n. That's how you write it when you're writing algorithms. Don't just think of it as n equals n plus 1, okay, for all practical. But when you're writing algorithms, you don't write n equal to n plus 1. You say set n as n plus 1. It's just don't worry about it. Just think of it as n equals n plus 1. That's all you need to know. But you don't write n equals n plus 1. But that's what we do. Okay, so that's the optimal policy. So what I want to do now is sort of solve a little example from the textbook to give you guys an idea. And for this chapter, the problem set will be, I'm going to grade your homeworks in this week. So I'll give you the homework 3, the problem set 3. Okay, what I want to have, 9.3, hold on, let me see what I want to assign as the homework. Okay, this will be a homework, the problem set 3. Let's write it here. B, and what one B and C. Okay. believe that should, can I get a textbook from someone? Real quick. Thank you. And that will be due along with your final exam. B and C, B, C, and D. Make it B, C, and D. And 9.3. B is fine. 9.2. B, solve using both policy iteration and value iteration. Okay. That should really take care of the homework. Can I hold on to this for a little bit? Okay. So what I want to do now is I want to solve an example. There's a repair person example that I want to solve. Okay. Let's look at page 158. Page 158, example 9.1. Okay. Example 9.1. Okay. Let's read that together to get an idea of what they're saying. Let x equals x naught, x1, and so on be a stochastic process with a 4-state space where E is A, B, C, and D. This process will represent a machine that can be in one of the 4 operating conditions denoted by the states A through D, indicating increasing levels of deterioration, just like our car example. As the machine deteriorates, not only it is more expensive to operate, but also production is lost. Standard maintenance activities are always carried out on states B through D so that the machine may improve due to the maintenance. However, improvement is not guaranteed. In addition to the state space, there is an action space that gives the decisions possible at each step. Okay? So each time you find the car in one of these states, you take a decision. And the decisions are, we sometimes use the words decisions and actions interchangeably, which is fine. In this example, we shall assume this action space A is 1 and 2. That is, at each step, there are 2 possible actions. Use an inexperienced operator, which is action 1, or use an experienced operator for action 2. So obviously, when you take those decisions, your transition probabilities will change, right? If an experienced guy repairs a car, the probability of it breaking down might be little, right? The transitions would be different. But if you have an inexperienced operator, the transition probabilities would be different. So you really want to find, and obviously when you're using an experienced repair person, there are higher costs associated. If you take it to a really nice repair shop, then the costs are more. If you take it to the down your street, might not be as expensive, but the transition probabilities will be different. So in that case, how do you make the optimal decision is what the problem is talking about. Okay. So for our example, to complete the description of the Markov decision problem, we need a cost vector and a transition matrix for each possible action in the action space. For our example, define the two cost vectors and two Markov matrices as follows. Okay? So let's sort of write this stuff down and then see how value function or value iteration algorithm works. Okay? So in this chapter, I'm not going to ask you guys to code. I did before. I'm not going to do that now. But all I want to do as part of the homework problem is really find 3 updates of the policy iteration algorithm or the value iteration algorithm, okay, by hand. Okay, that's what I wanted to do. Yeah.
Would you happen to know the difference between last year's textbook and this year's textbook?
There should be no difference really, unless the pages are on the other side or something.
Well, I only have 191 pages.
You don't have 226?
No.
Is that the last year's one?
Yeah.
Okay, I can make you a copy of it. Why don't you stop by after the class?
Okay.
Does everybody else have those pages?
Well, everybody else probably has this year's
Sorry?
book.
I have last year's.
Oh, okay. So are you looking at, I think she's saying
you're
that.
talking about the top.
Yeah, this one.
Oh, okay.
I don't know what that is. I think that's the count in the overall number of pages, I think, in the textbook. See, what this book does is really, it's a copy made from another textbook, which is really out of print. Okay? So the 226, I think you found it now, right?
Yeah.
Okay, good. Okay. So it really is extracted from another textbook, which is out of print. So I think they added their own numbers in the bottom to facilitate the transition from pages. But just look at the top page. That's what I'm talking about, or 158 if you want. Okay. So F1 here is the what is called the cost associated with using the inexperienced repair person. Okay. And F2 is the cost associated with the experienced repair person. As you can see, the costs are different, right? This guy is more expensive. Okay. And P1, the transition probabilities are also different. Okay. 0.1, 0.3, 0.6, 0, 0.0, 0.2, 0.5, 0.3, 0, 0.1, 0.2, 0.7, 0.8, 0.1, 0, and 0.1. Okay, that's sort of the transition probability of using the inexperienced operator. Okay. What is P2? And A, B, C, D. That'll be 0.6, 0.3, 0.1, 0.0, 0.75, 0.1, 0.1, and 0.05. 0.8, 0.2, 0.0, 0.9, 0.1, and 0.0. Okay. Now let's use the discounted. Okay, we want to use the value iteration algorithm that we just stated here to find the optimal values. Okay. So once you write that down, let's begin here with step 1. Okay. What is step 1? I want to initialize the value function vector. So V at step 0 will be 0. How many states are there in the system? 4 states, right? So I'll have a vector of 4 zeros. I'm initializing with 0. You can take any value, it doesn't matter. You can begin with a 0. Okay. And then I want to say beta is 0.95 and epsilon is, let's say, 0.01. Okay. And I want to initialize my n equals 0. Okay. N is 0. So then let's go to the next step. What is the next step saying? Next step is saying Vn plus 1. Let's go to step 2 here. What is n? N is 0, right? So we are looking at V1 of I equals, in this case, we're talking only about the cost, right? It's the cost of the system that we're looking at. Are we looking at cost or profit? I don't know what we're looking at. Repair person, so cost, okay. So you want to minimize that cost. Minimum A in AI R of IA plus beta summation P I A J V. What happens here? Vnj. So that will be V0j. Is that correct? V1I is what we're doing. The first step, the n here is really your step counter. Okay? So you want to write this as 1. V1 of I. And you're using your old value function that you already initialized over here. That's this guy. So you're beginning with an arbitrary value and you want to iterate to the optimal value. Okay? So what will happen here? I want to take what is, let's write this very clearly here again, equals minimum A in, what is the action space here? What are the two possible actions? 1 and 2, right? You can take A should belong to this set 1 and 2, R IA plus beta J in E, the state space, probability IAJ V0J. I'm just writing it again. That way we know what action to choose first. You want to try this over both values, right? You want to find which is the best action to take in that particular state. All I did was simply expand from here to here. Let's go a step further here. Minimum A in 1, 2. Let me try action 1 first. Okay? So what will that be? R, and I want to try on the left-hand side, write V1 of A. We want to first find the value in step 1 of state A. Okay? You have 4 states in the system, A, B, C, D. I belongs to that state space. So I want to first try V1A is this guy. So V1A is minimum, A in 1 or 2. R of, what is I here? Is A. What is the action? This is a little confusing just because the problem description is not that clear, okay, because they used actions 1 and 2 and it says A, B, C, okay. But A is really the action, and we want to try action 1 plus, what is beta? From there, 0.95, summation, J in E, probability, what is I here? A. What is A here? 1, J, just leave it as J for now, times, what is V0J? What is that vector? Isn't that simply 0, 0, 0, 0? Okay. So summation, what is P of A1J? Tell me that. P of A1J. Probability? Isn't it this guy? This whole row? Isn't that what it is? I'm using action 1. I'm in state A. These are the potential transitions to all those states. Are you guys with me? Everybody. So what does this essentially boil down to here? This PAIJ, this whole thing essentially boils down to, can you tell me the first row of that matrix, please? 1, 3, 0.6, 0. Thank you. That is what it boils down to. Is that right? The expected value, guys, nothing fancy. The probability times the value, the expected value, that is all this is. Oh, where am I running here? See, this guy right here is really the expected value. These are the set of probabilities. This is the values. Okay? And you have the beta before. Make sense? Okay? But are we done for this state? No, right? We only tried one action. How about the other action? Because if you want to find the minimum, I want to try both actions and see which gives me the minimum cost, right? So make this parenthesis real big here. Okay? Next action now. Isn't that the same as R? But you're in the same state still. You haven't changed the state. In the same state, you're trying both actions to figure out what is a better one. So R of A, 2 plus 0.95. Now what will this be? Tell me this. What will this guy be? Where do I get this row from? What are those set of probabilities? I'm taking action 2 now. Absolutely. 0.6, 0.3, 0.1, 0.0. 0.6, 0.3, 0.1, 0. What will be this guy? 4 zeros. The value is still 0. Everybody with me? Everybody on board, guys? Very straightforward. All I'm simply taking, since I'm taking action 2, and I'm saying that my starting state is state A, I'm using that entire row because I really want to find where all I can go to, times the value, right? It's simply the expected value. So that's your value for state A, the value function for state A. So what will that be? Essentially, what does this boil down to? Since this time 0 will be a 0, 0 times this is a 0, what are you left with? So V1 of A is nothing but minimum of, what is RA1? Look at your F vector. The F is the immediate cost vector. What is RA1? State A, state B, state C, state D, state A, B, C, and D. The cost of using repair person 1 in state A is $100. Is that correct? So this guy essentially boils down to $100. Now tell me RA2. If I use the second repair person, when you're in state A, the cost is $300. So this whole thing boils down to the minimum of 100 and 300. Everybody with me? So what is V1A? So V implies V1A is simply $100. Okay? Let's move on to the next state. We are still on iteration 1, mind you. We are still in iteration 1. In fact, we are still in step 2. Okay. Now, I got 100 there. V1A is 100. Now let's analyze what V1 in state B will look like. You're still trying to find the value in step 1 in state B. What will this be? The same deal, right? I want to find the minimum. This will be RIA, which will be R. What is I? B1 plus beta times, let's write this step clearly, that way you guys can go back and take a look at your notes. B beta summation P B1 J, I'm going to say J in E, V 0 J. Is that correct? Is that correct? Okay. And your other action will be, what will be your other action? Because you want to minimize over A in 1 or 2, right? What will be your other action here? R of B comma 2 plus beta summation J in E probability. Starting state is B, the action you're taking is 2, and your ending state is J, and J goes across V0 J. Right? This is what you want to do. This is what you want to analyze here. You want to find the minimum of those two guys. Yes?
Is it always V0J?
Yeah. The reason is, see, when we begin, we are saying that we set n equal to 0, right?
Yeah.
So in the first step, this n can be 0. You can begin with 1, 2, it does not matter.
Okay.
You can say V1, but your first step here will become V2. It's the same thing. You're basically using an initial value from before that you initialized when you started the problem.
Okay.
Okay, you want to begin with an arbitrary value and sort of, use that old value to see where you're going to go.
Why wouldn't this be V? Oh, I got you. Never mind.
We are in the same state
Yeah,
still.
I got it.
Yeah, we're in the same state. So that's why we don't go to V2 yet. We'll go to V2 in the next instant like that. Okay. Once we're done with all this stuff here, we'll go to V2. Okay. So tell me this guy. What will this be? This will be minimum A in 1 comma 2. What is R of B1? $125 plus beta times, what's this guy now? P of B1J. Action is 1, starting state is B, so I use this guy. Everybody on board? So 0, 0.2, 0.5, 0.3, the value function is still 0, right? The value function is still 0 because the previous step we initialized it with zeros. How about this other step here? This is 125, so what's RB2? That's 325 plus beta. Well, replace beta with 0.95, that way you guys are not wondering what this beta is. Since we assigned a value already, call it 0.95. And what will this be? What will PB2J be? From your, I raised it here. Can somebody tell me, please?
0.75.
0.75.
0.1.
0.1.
0.1 again.
0.1.
0.05.
0.05. Wonderful. And then you have 0, 0, 0, 0 here. Right? So essentially, what does this boil down to here? So V1B is the minimum of 125 or 325. And that will simply be 125. Okay? Okay? let's go here. Erase this guy. Tell me when you're ready. I don't want to. Are we done? No, right? We still have 2 more states to check with. Okay, and this is the reason you write a MATLAB code for this stuff. Okay. So what's V1C here? You want to find V1C. Help me out here, guys. I want to find the value at iteration count 1 for state C. Again, the same idea. Minimum A in 1, 2. Let's write this equations carefully here. What will this become? R C1 plus beta summation J in E P. What's your starting state? C. Your action 1 J times V naught J. Oh, I don't need this. Okay. Or your other value could be C, and I take action 2 plus beta summation J in E P of C 2 and then J V naught J. Okay, so what will this turn out to be? This will simply be the minimum A in 1, 2. What is R of C1? R of C1? Okay, somebody tell me. 150? Okay. 150 plus 0.95 times, what will this guy be? What is P of C1J? That will be the third row of your first transition probability matrix. 0.
0.1, 0.2, 0.7.
Thank you. And this guy will still be all zeros. And the other one, I believe, is 350, right? 350 plus 0.95. Tell me what this is.
0.8,
0.8.
0.2, 0, 0.
Wonderful. Okay. And this really boils down to minimum A in 1, 2 of 150, comma 350. So V of 1C is $150. Okay. And just from your observation, what is V1D? 500, right? So the first iteration in value iteration algorithm is, you can just pick it, from just looking at the reward vectors, because the value function vector is 0. Okay. So when I say 3 iterations, your first iteration is like that, right? Your second and third, you want to do it carefully. So I'm just going to write here similarly. We can compute V1D as 500. Do all these steps and you get V1D, which will be 500. The minimum of 500 and 600 will be 500. Okay? Now we are ready to go to step 3 of iteration 1. Okay? We are ready now to go to step 3 of iteration 1. That will be to check if we have reached the optimal solution. That is to check if we have reached the optimal solution. So step 3 says, check if V1I minus V0I is less than epsilon. So what am I essentially trying to do here? I'm saying 200, 125, 150, 500 minus 0, 0, 0, 0. Is this less than epsilon? Is this less than 0.01? No, right? So this is not less than epsilon. So every element here needs to be less than epsilon. That's your termination criterion. When you're checking for optimality, you want to ensure that, tell me intuitively what I'm trying to say here. When I'm saying epsilon is, let's say that equation gets satisfied, let's say when epsilon becomes equal to, it satisfies the equation, what am I really saying there? If Vn plus 1 minus Vn is in fact less than epsilon, what does that mean? Does it simply mean that my value from the previous step and the next iteration are not very much different? That's what it means, right? When you're subtracting those value functions, you're really comparing the values at two different steps, at let's say step 900 and step 901. If they're not that much different, it means you have the value has converged to the optimal solution. That's called convergence. Everybody with me? Okay, that's called convergence. That's what we're trying to do here. And this epsilon value is very important because it really stops the algorithm. The value you pick, if I pick epsilon as 100, or 200 in this case, or well, in this case it's 500, I would have satisfied, found the wrong optimal solution, right? So the epsilon is really a very small value that tells you when the algorithm has converged to the optimal solution. Okay, so this is very important. So this does not satisfy this termination criterion. So what do? Do n equals n plus 1 and go back, or set n equals n plus 1 and go back to step 2. So I want to go back. Okay. So let me, I can erase this guy right here. Okay. What is now tell me, how do I work with equation? Now go back to step 2. So now I'm beginning iteration 2 of the algorithm. Okay? You did n equals n plus 1. So where am I now? It's V2 of A, that is equals minimum A in 1, 2, R A1 plus beta summation J in E P A1 J V J, or V1. Now this becomes 1, right? Is that correct? Because I updated my iteration counter. So here it becomes 2. I'm using my old value. In the first step, this guy was 1, this guy was 0. What will happen in the next step? This guy becomes V3, this guy becomes V2. Okay. And what is the other step here? R of A2, because I want to try the second action, plus beta summation J in E probability A2J V1J. Okay. Now help me out here. This will be minimum of A in 1, 2. Tell me these calculations real quick. What is RA1? This was 100 again, right? That still remains 100 plus 0.95. What will this guy be? The same first row of the transition probability matrix. Remember, there's still a Markov chain underneath, so these transition probability matrices hold constant throughout. Okay, so what's the first row, guys?
0.1.
0.1.
0.3, 0.6, 0.
Wonderful, thank you. And what will this guy become now? This guy becomes 100, 125, 150, 500. So you updated your value based on your previous step. Okay? And what will this guy be? This will be 300 plus 0.95 0.6.
0, or no, I'm sorry.
Here's the first row of second
Yeah,
ppm.
0.3, 0.10.
0.6, 0.3, 0.10?
Yeah.
Okay. And this guy will again be 100, 125, 150, 500. Okay. You can use your calculator or MATLAB to do this computation real quick. And then I want to find V2 of state A will be minimum of two values, right? This guy or this guy, whichever one is the lesser one. Okay. Okay, it's 10:45, so we'll